Okay, so we looked at algorithms, and with these we're sort of stepping forward and stepping back, choosing which predictors to leave in. And at that one we use the p-value, but there's other ways we can measure how good our model fits. So let's go to the slides. We're going to call these measures. So the first one we're going to start with is what we call the root mean square, or if you don't square root it, the mean square error. And what this is sort of what you expect. We're going to take each observation and we're going to minus whatever value we get for that observation from the model. So this is the fitted value. That's our notation. We square it, we add them all up, we divide by it. So we're basically taking the average of the squared errors, or the mean square error, and then we take a square root. It's the root mean square error. And obviously smaller values are better. Simple as that. The other thing you could do is you could do the r squared, where what you're doing is you're looking at the correlation coefficient between your data. So here is the whole vector of my data and the fitted values, and we square that term. So you're just saying how strong do they correlate. More useful if you have obviously some sort of, well, you should have a linear relationship if it's working fine. But you know, if you had a lot of extreme values in this, you might want to use a Spearman correlation coefficient. The next one you can do is, instead of doing square terms, you could use absolute values. So you can think about this as your L1 norm. If you've done pure maths, you've got observed minus our fitted. We take the absolute value and we take the mean of that. And this is called the May, or the mean absolute error. The other thing you can do is with your adjusted r squared, we calculate r squared, and you can show, I'm not going to show that, we might do it in a tute, I can't remember, where you get the total sum of squares. So that's basically going to be all your observations minus the mean of the observations when we're talking about the response variable, minus our residual sum of squares, which is that thing we just looked at. It's the yi minus the fitted model all squared divided by the total sum of squares. And occasionally, to take into account large models, we can actually adjust that, and we call it the adjusted r squared. Again, closer to 1 with these, better. So now we're going to start, at the moment we've just been going sort of like, we've looked at some sort of distance between our observed and our fitted values, and we squared them. We want to start taking into account how many predictors we have in our model. Because if you think about it, if I just made my model bigger and bigger and bigger, especially over polynomial terms, I could eventually get it that it would fit the points exactly. And suddenly my distance between my observed and my fitted is 0. And we need to penalize that. So now we're going to start looking at is what we call penalized measures of fit. So we'll start with the CP estimate. And the CP, we're going to take our residual sum of squares. So what's our residual sum of squares? It's our observed minus the fitted all squared. We add them all up, which we've looked at before. We call this f hat, y hat in this one. What you can do is you can get a big model and use your big model to estimate your variance. And then we're going to have our residual sum of squares. So here's our measure of how good. But as we know, as our model gets bigger and bigger and bigger, this will get towards 0. But what we're doing is we're adding a penalty term. This is our first penalty term. We've got a term here that involves k, where k is the number of predictors. So the whole idea is this is our first example where we have some goodness of fit, which measures the distance between our observed and our fitted. But we're having a penalty term for the number of parameters to try and say, well, you can't get away with just adding too many. And in the next one, we'll talk about cross-validation, a really good way to take that into account. We've got our mallow CP. So again, we've got residual sum of squares. We're going to divide it by our sigma hat squared, which is going to be your residual sum of squares estimate from the biggest model you're considering. But again, we've got some penalty term here, which takes into account k, the number of parameters. But now we'll look at the big one. Quite a few times in the case studies, we've talked about AIC, or Akaike's information criterion, and this is the absolute classic. So, first of all, we don't have residual sum squares. AIC is for general models, and you won't necessarily have residual sum squares. So what we do is we look at our log likelihood evaluated to the maximum likelihood estimates. You can show in linear regression this ends up being the residual sum of squares, so that's fine. It's still got what we've got, but just looking more general. So this term here is a measure of how well our data fits. The more likely the data, the larger that number. So now bigger numbers indicate a better fit. So this is the equivalent of our RSS term, this one here, We need a penalty term, and here's our penalty term. There's 2k. So again, you've got a penalty for models that are too big, but a measure of how good it fits, and it's called the AIC. It's not very good for small sample sizes, so to do that we're going to do an adjustment. We take the AIC and we add an extra penalty term that takes into account and penalises really small sample sizes. This goes even further with the BIC, or the Bayesian Information Criterion. In this one they have a K, but they've replaced the 2 with log n. So what this is doing is taking into account how many observations you have in there. But all of them are saying they're what we call a penalised goodness of fit, where you have some measure of how well it fits, plus some sort of penalty term taking into account the number of parameters. And the whole goal is, with these, is we want the smallest value we can, and what you're doing is you're trying to find the smallest model that gives the best fit. Okay? So there's a whole load of measures. They're often built in. If you do data science with your next semester, we'll show that the yardstick package will do all these various measures to you. Which one you use? I must admit, I generally use AIC, is the classic one I use, or BIC. I find that BIC will often give me smaller models, and sometimes that's what you want. If you're a lot of predictors, you want a slightly smaller model. It's a clearer message. But I must admit, AIC and BIC are my 2 favourites, and they're very easy to get out almost any model. Okay, so that's it on measures. Next time, we will look at cross-validation. See you next time.